Welcome to 6.2. This is going to be a section on discovering how to find the area underneath a curve. And I apologize for the break that I had between 6.1 and 6.2. As a refreshment, 6.1 was all about anti-differentiation, or also known as integration. And if you can recall, anti-differentiation and integration are just the reverse of differentiation. Just remember that what we're doing now is working backwards from deriving. We're trying to underive basically. And in 6.2, in order to make this link between integration and the area underneath a curve, we are going to have to review some of our old summation notation calculations. This we tackled at the end of the year last year in pre-calculus, and we're just going to have to refresh on some of those. And then eventually what we're going to wind up doing is making a relationship between integration and calculating the area under a curve. This is the Greek letter sigma, and what it means to us in calculus is sum. What we're going to be looking at is kind of like a sequence of terms, and in this sequence of terms what we're going to try to do is add add the terms. So whenever you see this sigma, you should think, alright, I'm going to be adding up a bunch of different terms. So for example, I'm going to write an example down here. Alright, so just a quick review of what all this means. In the sigma notation, the complete sigma notation, what you're going to have is some sort of function that generates the terms in a sequence, so in a pattern. This right here, this 2i, is the formula that would generate every single term in my pattern. This right here is the index number that we're going to start with. That would be saying that I want to add up my first term and then plus the second term, third term, fourth term, all the way up until my end. So this is the start, this is my end term. Alright, so what this is really telling us to do is it's really telling us to take 2 times our first term, which would, our index number is 1, so we would actually put 1 in for that I, and then plus 2 times 2. Right, so this is actually a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub 5. And we're going to stop at the fifth term because that's what this indicates for us to do. And I'm going to be adding then, what would be my term 3? Well, this is once again the equation that generates those terms, so it would be 2 times 3. So this in all is what our sigma notation is telling us to do. So here are a few properties that I am going to also have you recall. If you have any kind of function, so I'm just going to call it f of, and there's a constant attached to it. So I mean, no matter what your index letters are, all the way up until we're going to just call it n, no matter what that your indicated values of, you can rewrite this as c times and then just calculate everything up. So I equals whatever all the way up to n, and then of your f of x. Okay. So for example, let's look at something like this. Okay, so pretty basic here, and then just know that this would have to match up with that I. All of what we're substituting in would go in for our index letter as indicated. So here, what I'm going to rewrite this as using my property is 3i equals 1, and then just of I. And so what this is all going to become is 2 times, and then now as I expand this out, it would be 1 plus 12. But what I also want to show you is you didn't necessarily have to use this property. If you just went straight down here and started rewriting this, it would be 2 times, and then here my index number is going to start with 1. What you're going to notice is you have this common factor in each one of these terms separated by addition. So what you could do is pull out that 2 and you would have gotten the same exact thing. So that's why that property works. Okay, and then also the sum and difference rule. All that states is if you're looking at two different if you're looking at the sum of many terms, so of some sort of polynomial, we're going to start at I equals something and then go all the way up to n, and you have, let's say, f of x or f of I. Sorry, this should have technically been an I, because remember, what we're going to do is be matching up some sort of index letter. Once again, the index is just some sort of variable that we're going to be substituting these terms in for. So f of I, what you can just rewrite this as is, okay, and this also works for the subtraction. So if you ever have two things being subtracted or many things being subtracted, you can always break them apart term by term and find the sum of each one. So I'm going to be doing number 1 here, and this start, they're saying start with 1, and remember, this doesn't always have to be 1. It can be other things too. So you just have to go by whatever is indicated. And then we're going to be doing 2i plus 1. So once again, where we're going to be substituting in is for this I. That's where our variable has been indicated. And what it tells us to do is use the summation capabilities of a graphing utility to verify your results. I'm going to do both. So I'm going to use our properties first, and I'm going to break this up because we have many terms being added. I'm going to rewrite this as the sum. Okay, and then here, right here, we have a constant. So I'm going to rewrite this as 2. And then finally, I'm going to actually write this out. So it's going to be 2 times, and when I actually solve this, it would be 1 plus 2. And plus, here, this one's a little interesting. Every single term from 1 to 5 is just 1. This is the equation that generates every single term. Notice there is no I to be plugging in. So really, all it's going to be is the first term, a sub 1, would be 1, plus our term 2, plus our term 3, plus our term 4, plus our term 5. So you would just have to solve all of this out. It'd be 2. And now I am going to teach you, and we'll come back to this, on how to do it on your calculator. So on your calculator, communicate this somehow to it. And in order to communicate that you're trying to find the sum of a certain pattern from here to there, you're going to have to indicate and type into your calculator that you want the sum of the sequence or of a pattern of a certain, whatever that function is that generates each one of those terms. You're going to have to specify the variable that you're using. Here they're using n, but our calculators, we most of the time just use x because that's the most available to us, easily accessible. You're going to have to tell you your start, your end, and then also what you want to go by. What's the intervals in between? And we're just going to go by integers, so we're just going to be going by whole numbers. So this is always going to be fixed at 1 for the purposes of what we're using it for. So right here you can see how you can enter in your sum. To tell your calculator that you want a sum. So if you were, for example, trying to do this right here, indicate this into your calculator, you need your sum and your sequence, because that's what this is saying. You're going to be adding up the terms in a pattern. And then what you're going to be doing is indicating the specific equation or the specific function that's going to be generating each one of the terms that you're interested in. And then this is your start, so you'll see here they started at, oh, I'm sorry. And then so here we used x. Alright, so then you just have to tell your calculator, hey, I'm using x. And then we're going to start at 2. So here's our start, here's our end, as indicated by that notation, and we're going by ones. Alright, and here would be what you would get. I am going to look back at this other example. How you would do this on your calculator is like so. You would need sum. Alright, example number 7. What 7 asks you to do is just write this so that you're writing this indicated sum of a bunch of terms in sigma notation. So this is what they gave us. Okay. So as you write this out, what you're going to notice is here, this term right here is constantly changing in a certain pattern from 1 to 9. And we are adding up these terms. Right away indicates that we are taking the sum of, and then the equation that generates each one of those terms. It's this whole thing right here, except for the fact that we have this piece changing each time from term to term. So I'm going to rewrite it as 3 times I. Okay, and then we're going to say I is equal to, and then we started at 1 and we ended at 9. Done. We had this one period of time where we were learning proofs by induction. So I'm not going to go into the proofs of why these work, but just understand that these are these summation formulas. Instead of rewriting, so for example, when we did all of this work right here, instead of rewriting all of these term by terms out, or also instead of just doing it on your calculator, we have these shortcuts that tell us exactly what these sums will equal. So for example, this one is if you're taking the sum of some sort of constant number. Remember, this is actually what we came across just a little bit ago. The idea is instead of saying, all right, each one of these would be 1 plus 1, you can just go ahead and say, well, whatever that number is on the top, that's how many terms that we have. From 1 to 5, we have 5 terms being added. So we could just take this number 1 times however many terms are being added, and then we would get time or equals 5. All right, so here's an example of that. All right, let's look at something like this. If you ever had, what we're saying is normally you would have to say 1 plus 2 plus 3. Otherwise, what you can go ahead and do is just understand that this is the number of terms that you're adding. So since I'm doing 1 to 5, it'd be 5 minus 1 plus 1. So there'd be 5 terms total. We can go ahead and just say 5 squared plus 5 all over 2, and this would get us 30 over 2, which is, yes, just 15. So by simply plugging into this formula, you don't have to kind of expand this whole sigma notation out. You can just quickly plug it into this formula. And all of these formulas are in your book. In your book, they just give you, they just give you the sum of some sort of number, some sort of index variable letter from 1 to n. They would say is equal to this right here. But what I do want you to focus on is just distribute this all out to get this. All right. Same thing here. If you ever have some sort of variable, some sort of index, remember index is just a variable, index variable that's getting squared, then you can just rewrite this all as that expanded form. And then an I cubed, here we have it, expanded form and everything. It would equal this. This is what we would have used by proofs of induction to prove, but we're gonna be using this instead.